Our next speaker is Max Heiber from Meta, and he's going to talk about something quite different. We are still looking outwards from our dynamic languages, but this time with the help of gradual typing and to support tooling.
Thank you. So do I just put it in the hole?
Yeah, I hope so.
And then, I have. I see. It's giving me another monitor. Sorry, just a moment. Whoever saw that, thank you for the sharp eyes. Okay, I just need to tell it that there's another display. I hope all the other talks were this entertaining. I want to turn off mirroring.
Maybe it's hidden. Yeah.
And we're good, we're good. So I'm going to be talking about telling the truth at scale, technology that we used at Meta. I wanted to say that if you have any hard questions, by the way, can everybody hear me? Yeah. If you have any hard questions, Andrew, could you raise your hand? That's the person to ask the hard questions to. So we work on the hack language team at Meta. None of the good ideas in this talk are mine. They're from these people who are also at Meta. So sound dynamic is I want to explain why I'm here, like why I'm talking about this. I think it's a new point in the design space of languages that are not fully static, what's sometimes called gradually typed languages. And I think that this is just the beginning. So if you're interested in these ideas, there's a lot more theoretical and practical work to be done to go further with these ideas. So I'm hoping people in this room can pick up some of these if you find them interesting. So in order to understand why we chose this solution, I think it's important to understand the context, the particular problems that we were solving. This is the Dynamic Languages Symposium, and I think there's a place for dynamic languages. I can say why hack, our language, got less dynamic over time. So we have much more than 10 million lines of hack at Meta, most of it in just a single code base. So you can see how it might be difficult to make changes. Hack evolved from PHP, a language that was once fully dynamic. And some features that are relevant for this talk is that hack has static type checking with generics, and it also has shallow runtime checks. And I'll say what those are soon, very soon. So when I say shallow runtime checks, I mean that if you call this function foo, by the way, there's a $ in front of variables and parameters in hack, just something we got from PHP. So if you call foo with something that's not a string, you will get a runtime failure. If you try to return something that's not a vector, where we've annotated vector in the return position, you will get a runtime error. However, we don't check deeply. So in the code here, you can see that we're actually returning a vector. Do I have a pointer? We're actually returning a vector of string, and we're claiming that it's a vector of int, and the runtime will not catch this. And actually, in this example, before sound dynamic, you wouldn't get any type errors either. Because foo, there is no type annotation on the return position. So this is an example of the interaction of untyped and typed code. So it's like foo returns a t-any. So t-any is a type that can be used anywhere. It might be familiar if you've seen Python with mypy or pyr, or TypeScript or Flow. A lot of these languages have this unlawful any type that you're allowed to use anywhere, and it can be useful for interoperating between static and dynamic code, but it's unsound. So we're going to present an alternative to t-any later in this talk. So I think hack is great. It's got static type checking, it's got runtime checks. However, the types can still tell lies. So here's a case where the type checker is telling the user via this hover, x is an int. I know statically x is an int. but unfortunately it's wrong. X can turn out to be a string at runtime. And I think it's interesting. Feel free to ask me later in the question section about more sources of lies. When I say a lie, I mean statically we think something has one type, but at runtime it turns out to have another. One source of lies that you've already seen is untyped code. But there are also escape hatches and dynamism, and this is true for most gradually typed languages, that they have these sources of lies. So what's the problem? Yeah, this is where we infer a T-any type. What's the problem with lying? Why do we care that types used to be able to lie in hack? Well, we actually hit some real problems at Meta with lies. One is that when something goes wrong at runtime, it can be hard to find out why. You don't know which types are trusted and which are not. Sometimes they're helping you and sometimes they're lying to you. But also, we rely on a lot of language tooling, and this language tooling can be very limited when the types are not trustworthy. So here's an example of what happens when you rename a function at Meta. We don't really rename it. We keep the old function around and we put a deprecated marker on it, and then we make the new one. Because due to the lies and due to dynamism, we don't actually know for sure that that function isn't called. And we try to have our tooling not do too much unsafe stuff. However, some of our tooling did unsafe stuff anyway. It's really hard to weed the stuff out. So we had a lint against redundant casts. So here somebody is pulling something out of a vector, and they're casting it to an int. Why would you cast an int to an int? The linter says this is stupid, you should remove this. But if you listen to the linter, who knows? Something bad. You might get a sev, and this is the sound of a sev, which is when Facebook goes down. Because of the linter told us that the cast wasn't valuable when in fact it was, because as I explained, our runtime checks are only shallow, so we're not actually checking at runtime that we have a vector of int, it might have floats in it. And try to avoid those things. So I'll stop doing that. It's just, runtime type errors are just very painful. It doesn't mean I need to cause you pain though, so I'm sorry about that. So there are some solutions that we considered to this problem of types that lie. One is doing full runtime checks, and that's what C# does, and that was some applause for C#. But unfortunately, we couldn't do that because with our 10 million plus lines of code that run in some of the web's most valuable properties, I think, we can't really do much to change runtime behavior or performance characteristics. So it's a pretty invasive change, changing what the code means in order to add more runtime checks, and we just couldn't do it. But there was a new option on the table, which is sound dynamic, the topic of this talk. So with sound dynamic, types tell the truth. This is a claim about the relationship between syntactic and semantic types. So syntactic types are the ones that the users write. Semantic types are what those types represent. And you can think of these as roughly sets of values. An important type here is dynamic, and it's not T-any, it's a sound alternative. So dynamic is a tool that lets users move from the untyped world to the, between the untyped and typed worlds using an upcast to dynamic. And we'll see this with code examples. Just check the time real quick. So before I get into these code examples, I wanted to explain something about hack. This is just a minor syntax thing that will keep these examples succinct. This is called a promoted parameter. And what this code here means is that when you call the constructor, we create a property called item of type int. So you can think of it as desugaring to the code at the bottom. This is not the most innovative thing in the talk, but it does make the examples easier to read. So here's a class intbox, and we think of this as having an invariant. You can see it on the line with the constructor. An invariant of intbox, for it to do what it says it does, for the type not to lie, is that item is always an int. So I'm going to talk about preserving an invariant. We want to check that this invariant is preserved. The item is always an int. So on the first line, we call the constructor. The invariant is preserved because we've just assigned the number 3 to item. Item is an int. Everything is good. And again, parameters are checked at runtime. So if we happen to sneakily try to put something other than an int in there, the code would have failed. On this line, the user is upcasting to dynamic. They're opting into dynamic operations. And this means that for our purposes, you can do most things with this variable BD, this dynamic box. So we call the set method on BD, which at runtime is an int box, and we try to set the item to a string. Just take a second to think like what you think should happen when this line of code is run. Exactly, you got it. Exactly. And that's what, oops. Exactly. Because the parameters are enforced, you see that set has this parameter that's annotated as int. We know that there's a runtime error here, and so the invariant is preserved and the last line is never run. So this is code that has a runtime error, but type checks, because the important property for us is not a relationship between the syntactic types and runtime behavior. It's between the syntactic types and semantic types. Here, no types are lying. Here's a harder example. Take a moment to think about whether this code should type check. The whole thing. So we have this, we have declaration site generics, and an important thing to know about generics in Hack is that they're erased before runtime. And this means that you can't check a generic type in a parameter because it's not around. The runtime doesn't know about them. And we have an invariant here. Our invariant is that item is of type T. Is this invariant preserved by the code? I'm not asking for an answer, just to think about it for a moment. It's not, it wouldn't be preserved if we allowed this code to type check. So our type checker rejects this code. It rejects this line that's highlighted in red. Because we have no runtime checking to ensure that the invariant is preserved. If we were to allow BD to, if we were allowed to cast a box int up to dynamic, then we would have no guarantee that when methods are called on it, they are checked. So if we allowed the set method to be called on the next line with the foo, that would actually go through, and item would be supposed to be an int, but actually a string at runtime, and that's exactly what we want to avoid. So the really important thing here is, I said that in a very convoluted way, but I think it's better to think about what happens with the intbox example, which is that it's the enforcement that enabled us to preserve the invariant, that the types are not lying. So I showed why this, on the face of it, relatively reasonable looking code with a box of T couldn't type check. So how are users actually supposed to write box of T and then use it? That's a problem to be solved. So we're sound, but so far not very expressive. That's a clap for how sound we are, but I think they should withhold their applause until we add back some expressivity. So the way that we did this is with like types. And so if users can't write types that tell the truth when they say that item is of type T, maybe they can tell the truth when they say that item aspires to be of type T. So when we put this tilde in front of something, we pronounce it a like type. A weaker invariant is that item has type like T. And this is just sugar for T or dynamic. So we have union types in Hack. We don't let users write them in very many places, but they're in the type system. And so what is still true is that item either has type T or type dynamic. So the following code is safe. And what's nice about this is that it's not so different than the other code, but we're a bit more honest about what can be known and what cannot be known. And what we could have done is, instead of like types, we could have written dynamic everywhere. So the constructor takes a dynamic, get returns a dynamic, set takes a dynamic. But then we've lost the ability for the user to tell us what the types aspire to be, what their intent for the code is. And we've also lost the checking that, yeah. So on the last line here, we still fail because we're returning something that's not an int, and we said it would be an int. We get the return type enforcement fails this code. But at no point do we lie, which is exactly what we were going for. Lies were the problem that we were trying to solve. And we enable expressivity by letting users express weaker invariants.
But when the return type is like T, so isn't it perfectly happy to return a string?
Return type is like T. So I was talking about the last line of foo.
Right.
Good question.
The return type of get is like T.
Yeah, but the function wants a T, an int. So you can't. The return type of foo itself.
Oh, it's the return that fails, not the call.
That's right. Yeah, thank you for that. That was important. Okay, so the problem that we had was that the types were lying, and now the types tell the truth. And this sound dynamic technology is used in our IDE features. It's used in our static analysis. We no longer have a linter that's telling people to remove casts that are actually very important at runtime. And what's next for us is to give users fine-grained control of dynamism. So we do have a lot of like types now. We would like fewer of them, and we want to give users tools to opt out of dynamism where it's important to do so. This has been modeled in Coq. There should be a paper coming out soon. And I want to briefly say what I think the next 20 years looks like, which is always very speculative, but I think worth doing. I want to point out that it took about 20 years for us to get here, where the world's most popular industrial dynamic languages are starting to adopt some static type checking with varying degrees of depth. And a few of them have shallow runtime checks or experiments with shallow runtime checks. So I think in 20 years, we'll probably see more runtime type enforcement, deeper adoption of static type checking, but also more work on the relationship between the runtime and static type checks, like the sound dynamic technology. I think if you have these two levels of type checking, it's important to be able to relate them in a meaningful way. And also I want to point out that to even explain what sound dynamic does, I needed to allude to semantic types, which is not a very common thing to talk about. So I expect in the next 20 years, we might talk about semantic types more. Now we're ready for questions. Thank you.
Thanks, great talk. For historical reasons, I really like types. Can you tell us what your users think of this addition? Or any, do you have insight whether this will be adopted, liked?
Yeah, that's a great question. I should point out that we were a bit subtle in how we rolled this out. So I didn't get into details in the talk, but we used this technology, implicit pessimization, which means that for this box thing, I'm having trouble going back slides. This is not what it actually looks like at Meta yet. It was just a bit hard to explain. I didn't go into too much detail, but I'm glad you've asked about it. Users do not write squiggle T. However, when they hover over something in their IDE, then they see the squiggle T. So the way we've explained this for our first stage of rollout is that the type checker is giving you more information so that if you have a runtime exception, if you're trying to figure out what happened, we tell you which types were trustworthy and not trustworthy. So the only place users see it now is in error messages and in hovers. And I think overall the response has been positive. I think our power users get it. It was, there were some bugs to be fixed, of course, like when we were overly liberal with where we put the like types or when our error messages were confusing. So there were a couple weeks there where we had to iterate, well, not me, but the people who did the real work had to iterate very quickly to make users happy. And since then, I think they like it. Yeah.
You mentioned union types. I assume for this to work, you also have intersection types. And if yes, can you say anything about that? Particularly in the context of intersecting function types.
Absolutely. Yep, we have intersection types. They're also used for type refinement. So if you have a union and then you do a condition that checks which branch of the union you are, inside the conditional, we know which branch you're on. And actually for this work, when we type check a function or a method, we type check the intersection of the type that the user wrote and a dynamic version of it.
I have two questions, actually. The first one is that I have not really understood why you cannot enforce a type for a generic. And the second question is that you seem to have motivated all this work because of the generic. Otherwise, you don't need this upcast dynamic. Is there another reason, or it's just that you have just mentioned this one for this talk?
Sorry, I'll answer the first question, then I might ask for a clarification on the second one. So for the first question, if we have generics, why don't we enforce the generic types? I wish we could. We can't because they're erased. So the runtime, when it does its runtime shallow type enforcement, it doesn't see those.
But why do you erase them?
Oh, why do we erase them? I think that's probably historical. So HHVM, which is the runtime for a hack, it evolved from a PHP runtime. And yeah, it's a good question. I'm sure there are other languages that erase generics. They probably have good reasons. And Andrew, can you?
I mean, yeah, it's historical. I think generics were added to hack as a static-only feature. They could have chosen to put it into HHVM, which is what they did with C#. But I mean, Java made the same choices as active. Many languages do the same.
Okay, and the second question I think is simpler. Is there another motivation for upcast dynamic than generic, or is generic the only motivation for this extension? If you were...
I see what you mean. I don't think that we would need any of this if we didn't have generics, because if we didn't have generics, my understanding is that everything would be shallow, like all my examples of. And if everything is shallow, everything is enforced, you would be able to trust all of the types.
So the conclusion, if you were not erasing types, you would not be needing all these, probably.
Yeah, that's right. I think there are probably other advantages to erasure. Okay, sorry. If we kept the generics at runtime and we wanted to enforce, you've returned a vector of floats, is every item in the vector a float? That's an ON check. So the C# model, I think, is different. I think things are checked as you put them in, which is a little bit better than deep checking everything as you go through. So depending on if we kept the generics around at runtime and we did deep runtime checks on every parameter and return position, I imagine it wouldn't perform well, but there might be smarter ways of doing runtime checks.
Hi, thank you for the talk. I can imagine at the scale of Meta, runtime performance is really important. So what's the cost of doing these runtime checks as opposed to not doing them?
I'm very glad that you asked. I'll say something suggestive. So there's a work by colleagues at Instagram for, let me see what it's called. Bonus slide. Oh. Well, I've lost it. Let me see. Okay, we'll go from memory. I can find you the reference afterwards. So at Instagram, they added static type checking to Python with runtime checking, and they got incredible speedups and can give exact numbers. And so this experiment has been done. I think, so adding runtime checks sped things up at Instagram, and something similar might be true for Facebook and Hack.
But I guess that needs cooperation from the VM.
Oh, yes, absolutely. So the runtime checks are done by the VM, and they enable a type analysis in the optimization for the bytecode. I'll just say it. Facebook would be a lot slower without shallow runtime checks.
Okay, thank you.
Any more questions? Then one technical question. I don't know whether you are an HHVM expert, but since you talked about shallow checking and the collections, does HHVM use storage strategies, which might be one way to get those checks fast or avoid them?
Yeah, you've caught me not being a runtime expert. What is a storage strategy?
It's basically you're trying to specialize on your erased collection, the type of the elements in the collection. So V8, for instance, uses that for integers or doubles instead of storing it all as boxed objects.
Yes. Yeah, there are quite a lot of types in the analysis. I think some of the optimization happens in the JIT, and some of it happens in a bytecode to bytecode compiler that sees the entire thing and infers the types. And so I'm pretty sure we don't box all the ints, I think. One thing I also know is that you mentioned V8. I know that V8 uses hidden classes so that when you're passing around JavaScript objects, it knows the shape of the objects and can optimize the layout. We do almost the same thing. It's the things are dictionaries according to what the user actually writes, but at runtime we treat them more like records, and that's through type analysis.
Okay, cool. Thank you. Any last question? Well, then let's thank Max.
Thank you.